Hi, my name is Rishi Banerjee.
My name is Stephen Chen.
My name is Mehal Kashyap.
My name is Sonia Purohit.
And my name is Gabriela Borla.
And today we will be talking about a comparative analysis of machine learning algorithms through credit card fraud detection. So I'm going to go through a little bit about our presentation first. So first of all, I will be presenting to you the purpose of our project. Then we will go a little bit into the background of data analysis and also credit card fraud detection. We'll go through our algorithms a little bit, and we'll also go through how we measure the success of our algorithms. Finally, we will talk about our results of this project, and we'll talk about a little bit about our future plans. So our purpose was to detect trends in credit card fraud and also predict credit card fraud, and also measure the efficacy of certain algorithms used for credit card fraud detection.
So with the rise of e-commerce, it's only fitting that credit card fraud is also on the rise. And put simply, credit card fraud is essentially the unauthorized use of a credit or a debit card, and it typically happens without the knowledge of the cardholder, and it's not necessarily limited to the theft of the physical card. So credit card fraud comes in two different types. You have card present fraud, which is when your card is physically stolen and then used at a certain location. But then you also have card not present fraud, which is when your credit card information is compromised. And that one's a little more dangerous because it's harder for the cardholder to detect, and also it's more of a growing problem because of the popularity of online shopping. But it's in the best interest of credit card companies to detect when a transaction is fraudulent or not in order to prevent monetary losses, and they do this using data science. So they try to generate a user profile. So this would be based on the user's purchase history, a location of purchase, and purchase amount to detect trends. So our project aims to use various machine learning algorithms and try to find the best combination of factors to analyze in order to determine whether a credit card transaction is fraudulent or not. So why do we choose credit card fraud? Well, it's a growing and prevalent problem, not just in the United States, but also worldwide. But within our country, analysts estimate that 43% of Americans have been victim to credit card fraud within the past 5 years. And the Nielsen report also claims that $24.7 billion have been attributed to credit card loss. So clearly there's a need, and this represents a 12% increase over the previous year. And you can see in these two diagrams, there's an increase in both the number of victims to credit card fraud, along with the amount of money lost. So given these trends, it's really imperative that machine learning algorithms get smarter and become more robust in order to meet the demand to detect whether a transaction is fraudulent or not. And that's exactly what our project aims to do.
So data mining is a large part of our project. Data mining is a process used to determine patterns and trends in large data sets. It uses skills from information sciences, statistics, and machine learning. Information sciences is a branch of computer science that deals with the analysis, storage, and retrieval of information. Statistics is the study of the organization and interpretation of data. And then we have machine learning. Machine learning creates computer models to recognize patterns in large data sets. And these patterns are improved on automatically and continuously. There is no need for any human interference. And this works very well with making predictions. Basically, an algorithm is given a training data set with target values, and it learns from this training data set so that when it's given a testing data set, it can make predictions. We are using supervised machine learning, which analyzes the relationship between the input and the output and also makes predictions.
Okay, so next we'll talk about procedure. All right, so shown above here is the dataset that we used for our research. This dataset came from a 2009 competition hosted by the University of California at San Diego and also the Fair Isaacs Corporation. It contains 94,682 data points. However, as seen above, there's several hidden fields due to the confidential nature of credit card information. And so we have 16 known factors, and these include the amount of the transaction, the hour at which it happened, and also the location based on the zip code. But there's also 13 unknown factors, and those are indicated by field names such as field 1, field 2, flag 1, flag 2, etc. We believe that this is a trivial issue, however, because our research project mainly focuses on detecting trends within the data set, proving that there are trends to observe when predicting credit card fraud. However, there are two other large issues that we face with the data set. The first issue is overfitting, which is a condition where an algorithm can only work with a particular data set. And the second issue is bias. So this data set in particular has only 3% fraudulent cases, which means that out of the 94,000 cases that are provided, there's only 2,000 that are actually fraudulent, which provides us only a small sample size to work with when making predictions. And so we try to solve these issues with data preprocessing. So in our first attempt to preprocess the data, we split the data set into two different data sets, one as a training set and one as a testing set. But the biggest issue that we faced with this was that the ratio of normal to fraudulent transactions within each data set was still 90-2, which is a huge ratio. And so it provided us with skewed results when we ran our algorithms. And so in the second time that we attempted data preprocessing, we decided to split the fraudulent transactions 50-50 into both the training set and the testing set. And by changing the number of normal transactions which we put into each compiled data set, that would change the ratio of normal to fraudulent transactions within each one. And so using this method, we were able to create 6 unique data sets to run our algorithms with, and ultimately we got much more precise results through this method.
So now I'll go into a little bit about our algorithms. Our first algorithm is the k-nearest neighbor algorithm, also known as KNN. So what KNN does is it plots the training data set, and then it plots one testing data set. And it finds the distance between all of the training sets and that one testing set. And then after that, it finds the closest distance, and it uses that closest distance to find whatever you're looking for, to predict whatever you're looking for. So for example, in our case, we're trying to predict fraudulence. And so let's say that this was our testing point and this was our training point, the closest distance training point. Let's say that this training point was fraudulent. We could also assume that this testing point right here was also fraudulent because this closest training point was most similar to that testing point.
Our next algorithm is the logistic regression. The logistic regression uses the logistic and sigmoid functions to perform binary classification. Binary classification is the simplest form of classification, and it has a target attribute that can have 2 possible values, for example, 0 and 1. This works very well with our data set because we have a binary dependent variable, which is our target variable. This shows with a 0 if it is non-fraudulent transaction and a 1 for a fraudulent transaction. What happens with this algorithm is when it is given the training data set, it makes a model similar to this, similar to the sigmoid function. Here, the x-axis is the log odds, which are calculated from the data in the training data set, and this is the output probability on the y-axis, which is between 0 and 1. This probability shows the probability of the transaction being fraudulent.
Okay, and so the next algorithm that we use is called the naive Bayes classifier. Similarly, it's a binary classifier, which assumes that every attribute affects the outcome independently. So it's based off of Bayes' theorem, which is provided below. And the Bayes' theorem provides a model to calculate the posterior probability, which is the probability of a certain outcome given certain pieces of evidence. And so in our case, the outcome would be the fraudulent versus non-fraudulent transaction, and the evidence would be the attributes that we provide based on the transaction.
So our next algorithm is the random forest classifier. What this algorithm does is it generates decision trees, which are a set of instructions that predict the trends in order to find and classify these fraudulent and non-fraudulent cases. So the structure of decision trees and the random forest classifier is beneficial because not only can it run one attribute by one attribute, like run field 1 by itself and then hour by itself, but it can run all of them as an ensemble and then rank the attributes by its importance.
And the final machine learning algorithm we use is called the support vector machine. And it works best on classification problems such as ours, where we're trying to classify our data as either a fraudulent transaction or a non-fraudulent transaction. And the way it works is it graphs all the training points on an n-dimensional hyperplane, or an n-dimensional plane. And then where n represents the number of factors that you're trying to analyze, so a factor being like the purchase location or the purchase amount. And then it tries to generate the equation for the best fitting hyperplane. And hyperplane is just a dividing line that differentiates between your 2 different categories. So then when you apply a testing data set to this model, it's able to classify it based on whichever side of the line the data points fall, and it's either able to classify your transaction as either fraudulent or non-fraudulent.
So along with these algorithms, we also apply deep learning techniques in order to try to classify our fraudulent and non-fraudulent data. One such example of this was the multi-layer perceptron network, which is one of the simplest forms of a neural network. A neural network is a data algorithm which is modeled after the structure of the brain and contains data structures called neurons and connections between these structures called synapses. A neural network is contained of many input layers, hidden layers, which find different trends and do multiple processes such as matching to a function, and an output layer. These are created in Keras, which is a Python API for deep learning.
So when measuring successes, we first turn to accuracy, but we found that accuracy is not a very good way to measure our success. For example, when we had the 98 to 2% ratio, we found that the algorithms were predicting all non-fraudulent transactions, but this still gave a 98% accuracy. So we turned to precision, recall, and F-score. Precision is the percent of all predicted fraudulent transactions that were actually fraudulent, while recall is the percent of all actual fraudulent transactions that were predicted as fraudulent. So in this diagram, the orange represents those that were predicted as fraudulent, while the blue represents those that were actually fraudulent. So the overlap is the true positives, that were correctly predicted as fraudulent. In this first section, there's low precision because of the orange area, less than half of it overlaps with the blue. There's high recall because from the blue area, most of it overlaps with the orange. In this second model, from the orange, almost all of it overlaps with the blue, so there is high precision, but there is low recall because from the blue, very little of it overlaps with orange. The last model here is the ideal one with high precision and high recall because the two areas almost entirely overlap. F-score is the combination of precision and recall, so this last model is showing the ideal F-score, the highest possible F-score.
Okay, so now we're going to talk a little bit about our results. So this graph represents the F-score versus normal to fraud ratio of when the training set and the testing set both have the same ratio. So for example, the training set and the testing set both have 50% 50-50 fraudulent to non-fraudulent ratio, or 1-to-1 fraudulent to non-fraudulent ratio. As you can see here, as the normal to fraud ratio decreases, which means as there's less normal but more fraudulent cases, the F-score increases, which means that the algorithms themselves, in this particular case, work better when you have a lower normal to fraud ratio. So for example, let's look at K&N right here, which is the red line. At about 1/3 normal to fraud ratio, you have an F-score of about 80%. But when you look over here at about 9-to-1 normal to fraud ratio, your F-score actually drops to 20%. The only algorithm that doesn't apply to this happens to be the support vector machine, which is seen right here.
So in our next trial, we applied this same technique, except instead of doing it with the testing set having the same ratio, it had a 98-to-2 ratio. Because in a realistic setting, you would create the model and then compile all of the data into the model. And all of the data would have a high skew. So as a result, we saw that closer to 50-50, there was actually not a very high F-score in all of the algorithms. Because when the algorithm was trained on 50-50, it expected that the testing data set should have 50% fraud, 50% normal. But this isn't the case, because in the testing data set, you'd have 98% normal and 2% fraud. As a result, we found that for many algorithms, there's an optimal ratio, as you can see in the random forest here, where there is some ratio where there's enough weight on the fraudulent data to predict the trends, and there is enough so that it won't predict It won't predict everything as 50-50 or some ratio.
So we had two main goals in this experiment. The first one was to determine the optimal combination of factors that a credit card company should analyze. And then the second was to determine the best performing algorithm. So in regards to the first goal, we determined that you get the best results if you analyze the purchase time, so the hour the transaction was made. And that was dependent on the F-score, which we saw was at a really high value for purchase time. In terms of the best performing algorithm, we determined that if you have a 1-to-1 ratio or close to 1-to-1 ratio of fraudulent to non-fraudulent transactions, the best performing algorithm was the random forest model, which is depicted right here because you have the highest F-score at a low normal to fraud ratio. But if you think about it, in real life, you have way more non-fraudulent transactions than you do fraudulent transactions, which means that you're not looking for a 1-to-1 normal to fraud ratio, you're looking for something way higher. So then in that case, we determined that the support vector machine works the best because it has the highest F-score when the normal to fraud ratio was significantly greater. So from this information, we were able to conclude that a credit card company should be using a support vector machine algorithm and analyzing the purchase time in order to most effectively detect whether a credit card transaction was fraudulent or not.
So we have two main future objectives with our research. Our first objective is to apply our machine learning algorithms to an unencrypted data set. So in that way, we can actually discover which factors specifically are the most important in detecting credit card fraud. And our second objective is to apply our knowledge and our research of data preprocessing to other research topics which involve a skewed data set. So for example, earthquake predictions, bridge disasters, or personal health safety all have really skewed data sets. And so we believe that our data preprocessing methods will be really effective in helping out these research topics. Overall, we believe that our research has very wide-ranging implications for future data science projects.
So we'd like to thank all these people on the board. Specifically, we'd like to thank Jacob Battipaglia, who was our project mentor. We'd also like to thank our project liaison Siddhi Shah. We'd also like to thank Brian Lai, who was the research coordinator, Nicholas Ferrero, who was the head counselor, Dean Eileen Rosen, Dean Antoine, Rutgers University, Rutgers School of Engineering, the state of New Jersey. Our corporate sponsors, Lockheed Martin, Silverline Windows, and Rubix, and also our the GSET alumni who helped make our experiences possible. These are our references. Any questions? Yeah, in the back.
I have a question. Just wanted to, say that's a great job you did. Seems a lot of vector methods in use. So did you guys learn linear algebra on the fly here? I know high school courses mostly don't cover that. How did that go?
Do you want to take it?
Sure. Well, we didn't really take any linear algebra courses, but we were able to learn about various machine learning algorithms and their implementations using Kaggle. So that's basically an online site that gives us real-world experience with taking different training sets and then applying them to testing sets. But we had a little bit of prior knowledge of statistics, which allowed us to have the knowledge required to understand precision, recall, F-scores, and all the various metrics that we use to determine the success of the various algorithms.
Okay, thank you.